Okay, we'll go ahead and get things kicked off here. It's right at 1 o'clock. So good afternoon and thanks for joining today. I'm Tyler Williams. I'm a Nebraska Extension educator located in Lincoln, Nebraska, and I'm host this webinar on behalf of the North Central Climate Collaborative, which is a part of the North Central Regional Water Network. And today's webinar is titled Understanding and Interpreting Climate Outlooks, and we're happy to have Mr. Jon Gottschalck from the Climate Prediction Center, which is within NOAA's National Weather Service. And he's been with the Climate Prediction Center since 2004, and he's the chief of the Operational Prediction Branch and is responsible for outlining the overall direction of operational forecasts and related activities. Prior to this, he served as the CPC Head of Forecast Operations, where he is responsible for overseeing day-to-day routine production and dissemination of CPC's operational forecast products. He earned his bachelor's and master's degree in meteorology from Pennsylvania State University. And so we're excited to have Jon here today. Before I turn it over, I have a couple housekeeping things here at the front end. If you have any questions as we go along, please go ahead and put them into the chat box, and I will monitor as that goes along. If something's pressing, they need addressed right away, I'll interrupt Jon and have him answer the question. But I plan to keep most of the questions until the end. But please type them in anytime so you don't forget what you're going to ask, and we can have some Q&A at the end. I'll also put up a couple poll questions. So at the beginning, you should see some poll questions pop up. Once you see those pop up, you can go ahead and answer, and I'll actually go ahead and pop them up now. So if you see those poll questions, just go ahead and click twice to tell us where you're from and how you might use this information. We use that as we assess the impact of these webinars. So you'll see another one of those pop up again at the end. Just again, 2 questions at the end. We'll get your responses. That would be great. This webinar will also be recorded, and we put that on the northcentralclimate.com website. And you can also go there to see previous webinars that we have every other month. So I think that's it. And so I'll go ahead and turn it over to Jon. And thanks again, Jon, for being here. Really appreciate it. And hopefully this works out for you.
All right. Thank you very much, Tyler. I really appreciate the introduction. And I also want to have a special thank you also to Dennis Toddy and Ann, who originally invited me, I guess about a month or 2 back. So I really appreciate the opportunity to be able to talk, provide this webinar for you folks today. As Tyler mentioned, I'm with the Climate Prediction Center just outside of Washington, D.C., and I'll be talking about some of our climate outlooks, and mainly we'll be talking about our longer lead outlooks, like focusing on the seasonal outlooks or forecasts, for example. If we go to this next slide here, which will provide an outline of what I'm going to be talking about today. I will spend just a few minutes providing just a very brief overview of our outlook suite in general. And the reason I just want to do that is, even though we'll be focusing on the seasonal outlook, as one gets closer to their target time period, there's other products at CPC that may be able to help with any sort of decision making or situational awareness as you move closer to your time period. The bulk of the talk in the second bullet there will be on the seasonal outlook products and services overall, and then we'll wrap up with some verification. We'll be able to show everything, but try to show a few things related to the seasonal outlook so you can get a sense of how well these outlooks do overall. So starting with that, what I have here is a pretty complicated table, but I'll walk through it with you. First, we do short-term outlooks as well, and the ones in the blue box there are temperature and precipitation outlooks for 3 different periods. It's one we do for the days 8 through 14 period. We do the monthly similar sort of product and seasonal, and I'll be talking mainly again much about the seasonal. But some of the specific details of variables, the type of product, the frequency, and the release date are provided there. And I'm not going to go through those details really for today, but mainly more to let you know about some of these other shorter-term outlooks that go on as you get closer to your event. And these are ones in blue are all temperature precipitation focused. The next block here in yellow are our drought outlooks. We have a monthly drought outlook that's issued at the end on the last day of the month, and also a seasonal drought outlook that's released as part of our regular seasonal temperature and precipitation outlooks on the third Thursday of the month, as you can see there. And finally, we do have a set of slightly different type outlooks, which are focused more on extremes. We're trying to move more and more in that area, provide more and more information as we can in that context. And we do have a week 2 U.S. hazards outlook for the U.S., and we also have a global tropics assessment that we release weekly. The U.S. hazards outlook is released daily. So just to kind of real quick provide an overview of some of those outlooks. I won't be describing everything that I just talked about, but one of the main things that I think can help as you get closer to some of the periods that might be interested in, where there's a little bit more signal to noise, that ratio is higher, is the week 2 period, or days 8 through 14. These are probabilistic for temperature, for example, on the left, and precipitation on the right. And these are for different categories. Tercels, I'll describe that a lot more later with the seasonal outlooks, but we'll be talking about the probabilities of being above, near, or below normal for either temperature or precipitation. And what's shown on these maps is the most favored category for above, below, or near normal. And again, this is for the weekly mean temperature, ending up in one of those 3 categories, or the weekly total precipitation amounts in one of those 3 categories. One can go a little further out with respect to more extreme type impacts, and we do have for our week 2 period where we're trying to get a little bit more granularity, if you will, about what the week 2, within the week 2 may hold. So we do look towards probabilistic forecasts of some hazardous conditions as we define them through various thresholds or exceeding various percentiles of the historical record, or both. And we do that for temperature, precipitation, and wind at the current time. And this just shows an example of temperature on the left from this past winter, and also precipitation on the right for this during parts of April. And you can see the risk areas are highlighted as either slight, moderate, or high, and that's based on calibrated probabilities from some of our numerical model guidance and other factors as well. And this is just to provide a little bit more detail within the week 2 period, and also trying to target any potential more hazardous conditions than just the weekly mean forecast that I showed earlier. And for a little additional lead time, we do have week 3 and 4 outlooks that we started issuing over the last few years. This is an example from a forecast just after Christmas of 2018, up on the upper left. Now, I won't go into this, but this outlook is a 2-class system. This was an experiment on our part to get feedback on whether 2-class versus 3-class system would be more understandable or easier for some of our users. And so we did go ahead and go that way for this particular outlook. But this is a very similar sorts of thing in the sense that it favors temperature and precipitation. But this is over a 2-week period, meaning we have 2 categories, either above or below, hence the 2-class, favoring the total precipitation amounts in either one of those categories, either above or below. And the same thing for mean 2-week temperature. And both these plots, again, show the most favored category. And just on the bottom are just how this particular event turned out, which actually turned out pretty well with respect to the outlook. So now moving towards the longer lead, which I'll be spending most of my time with, I haven't shown and won't be showing the monthly outlooks that we do, just because they're very similar in nature and description and interpretation as what I'm going to be talking about with the seasonal outlooks. But keep that in mind that we do a monthly forecast at the about third Thursday of the month. That's released, and also an update on the last day of the month. So moving towards the seasonal outlooks, we go to an example map, which is shown here. This is actually from the spring outlook for the period from April, May, and June 2019. This was issued in about the mid-March time period. And so the first thing I want to point you to is that we have the legend there on the bottom, which is related to probability. Indicates the probabilities for warmer than normal, which are the warmer shades, and the blue colors are for cooler than normal probabilities. And one thing to note that's important is that as you get towards the darker colors, all that means is the probabilities for that upper tercile, let's call it the above normal category, are higher than the climatological probability of 33% for a 3-class system, which is what the seasonal outlook is at the current time. It does not mean that the temperatures will be increasingly above normal from a climatological value in absolute terms. This is just the probability of being in that upper category or above normal temperatures as we define them. And that's also the case, for example, if you look all the way on the left-hand side with Northwest Alaska, which is where the highest probabilities actually are on this entire map, which are on the order of greater than 60, greater than 60% probability. Again, that's not in absolute terms. It's just the probability of the eventual seasonal 3-month mean temperatures being in that upper tercile or category of above normal temperatures. One thing that's also very important to note, which can confuse people, is the white areas. The white areas are designated what we call equal chances, and what that means is the equal likelihood of any one of those 3 categories is possible, or in our view. There's no strong climate signal or that would be reliable in our minds, that would give us confidence to tilt the odds, if you will, in a forecast either for above or below normal temperatures in this case. And so that's why we have termed it equal chances, meaning the probabilities for above, near normal, or below normal temperatures are all about 33%, since this is, again, a 3-class system. Now, one way that we've tried to improve that, which I'll get to in 2 slides, but just want to briefly show an example for precipitation, where things work exactly the same way. But this is an example with green and brown shades for the precipitation. And again, we have areas of white indicating equal chances, or a 33% chance of being below normal precipitation-wise, near normal, or above normal. So we basically equal chances in those areas. Whereas the Pacific Northwest would be favoring drier than average conditions, and much of the rest of the continental United States would be favoring above normal precipitation amounts for the 3-month period, April through June 2019. To better understand this, though, we have on our website more of an interactive displays for our seasonal forecasts. And this has been very important because for many, many years, and still to this point, people really are hindered, if you will, or focused just on the color. But on these static maps that I just showed, for example, on the previous 2 slides, they really can hide the fact that all of these locations on these maps actually relay information about the odds for all 3 of those categories. And that can be hard to understand. So what we've been able to do, with the help from our National Weather Service partners actually in the West Coast, have developed a tool that we've utilized here as well and modified it for our usage, is that if you take a look, for example, you can't really see it there because of the plus and minus with the zoom, but I clicked on an area in the Pacific Northwest where we had higher probabilities for above normal temperatures. And what's really being indicated on that map is what's shown there on the left. Significantly increase, about 2 times, the odds for above normal temperatures over that 3-month period as compared to climatology. And what you'll notice is that there's actually a very small chance or odds for below normal temperatures, a very small sliver of blue there, and with only about a 30% chance for near normal temperatures in that category. And so we apply simple rules overall where we take the probabilities away from the opposite category until we achieve about 3.3%. We don't allow any category to go to 0 for obvious reasons, and then we eventually take away from the near normal category. And so this is kind of an example for that one grid point or one area that I'm showing there from the black arrow. That pie chart is really what we're trying to convey. And so this sort of interface has helped a lot with our users understanding exactly what the outlooks are trying to convey. And if you go to the next slide, just a quick look of how things would be for that below normal temperature region for this particular outlook. And you can see the number of circles there in the Midwest or in the plains is significantly less. And so much of the probabilities for all three categories take up much more of the pie chart, even though below normal temperatures are favored, meaning an increase from 33% to 45%. There's still non-trivial probabilities for the other two categories. In fact, near normal odds for the near normal category are the same as climatology, and it's only a slight reduction for above normal temperatures in that region, even though the color on the map, the static map, for example, would be blue. And furthermore, if you go to the next slide, with respect to precipitation, it works the same way as shown on the bottom. This is the area across parts of eastern Idaho or areas in the Central Rockies, let's say, where the above normal precipitation, the category, is significantly increased to 58%. Near normal precipitation for the 3-month period still remains at its climatological value of 33%. But maybe perhaps more important for some folks is that the odds for below normal precipitation are much significantly lower than 33, closer to 9 or 10%, let's say. Now, just very quickly, the next two slides, just to note basically that CPC produces similar sort of forecast maps as I just showed for 13 different forecast leads, as we call them, which are overlapping 3-month seasons out to about a year. We do that for temperature, which is shown here, and also for precipitation on this slide, where, for example, in this particular case, the top row is for May, June, and July, and then July, August, September, October, and so on, all the way to about 1 year. As you look on the final row, it extends out to May, June, and July 2020. And of course, as one increases out in time, things become increasingly difficult. The signal to noise for some of the climate predictors that we utilize become increasingly difficult to identify and to have reliability for. But I just wanted to mention that we do extend out to about approximately 1 year or so. Now, moving ahead to some of the other side products that we have associated with the seasonal outlooks that we're trying to provide additional information than just the maps. The maps can get certain users ahead as far as what they can expect for the situational awareness and so on. But we're trying to provide a little bit more information than we have in the past. And I'll get to that like in a second. But one thing I did want to note, which sometimes can be helpful for some folks, is that we do try to explain in sometimes more technical terms, sometimes more layman terms. It kind of depends somewhat at times on the forecaster, but we try to explain the forecast basis, the rationale for the actual outlooks on temperature and precipitation that I was just displaying, for example. And we call that part of our prognostic model, prognostic map discussion. Basically, it's a text discussion that kind of explains the factors that are most relevant for this particular outlook. It's generally heavier weighted towards the first several seasons, but does include discussion about factors that may impact the upcoming summer or winter, depending where we're at in the time of the year. Now, one thing that is a very scary diagram to look at, and we're working on ways, which I'll show in a second, to improve how this information can be utilized. But even though the maps are static in that way that I've discussed, and also we have the pie charts, we also have a lot of quantitative information about the whole distribution, as we call it, about how the forecast is showing how the climatological range or normal curve, if you will, temperature or precipitation will shift in accordance to our official forecast. And one of those products is called the probability of exceedance. And I don't want folks to get too hung up on some of the scary nature of this plot on the right. There's a lot of information down there with respect to what the certain anomalies will be for various percentiles. And I'll explain a little better on the next slide how one could, in a basic sense, can use this diagram to infer additional information. But on this slide, I just want to show that basically this is a plot from a forecast, I guess, a few years ago now, but basically shows the anomaly in inches of the median value of the outlook distribution. So just think of this as the anomaly over that 3-month period for precipitation. And you can see the numbers are very small, which is not surprising, again, for both temperature and precipitation, since we're dealing with seasonal precipitation amounts or seasonal mean temperature. The anomalies that we see from climatologies are very small. That we're not talking about a day 1 or day 1 through 3 precipitation or temperature weather forecast. So it's important to keep that in mind as well. In this particular plot, the dashed lines are just the median value for the climatology, in this case 81 to 2010. And again, the shading are the anomalies from the climatological value. And so to take a look at this a little bit more clearly, or specifically, this is the area that I had highlighted, if you recall, in the Seattle area a number of slides ago for that probability of exceedance graph. And basically, just to focus on one thing from this graph that could help maybe help you understand the wealth of information that can be gleaned from this once you understand it. If one were to take a look at 58 degrees, for example, first of all, this black line here is the climatological distribution. The jagged yellow line is the actual individual years, and the black line is a curve fitting that, basically. And so in this particular case, if you were to take 58 degrees, at least in this particular period, climatologically for this area, that's at the 50% probability. Now, what's shown in the red lines is the impact of our official forecast on that distribution, and so the probability of exceedance graph, which you can see is shifted to the right. And if one were to look at that same 58 line and follow it past the intersection with the climatological black line, you would see you'd have to go all the way up to about 80% probability of exceedance. So there's an 80% probability of exceedance in this forecast of surpassing 58 degrees, whereas compared to climatology, that would only be 50%. And so there's a number of different values on the x-axis in which you can kind of get the probabilities or the probability change based on our official outlook from what would be expected climatologically. And so obviously there's a lot more that we can go through with this, but that's kind of how this works. And a similar example will be what's shown here, which was for precipitation. And again, if you wanted to take a look at a value and see how the forecast is, the odds for that value threshold changing with respect to our official outlook, you can maybe focus on the x-axis for 4 inches, which is down here, and you can see the probability for that under normal conditions, if you will, is a little over 40%, but with the outlook, that increases to almost just under 70%. So this whole curve is shifted to the right because it's a wetter forecast in that area, and so the probabilities of exceeding these thresholds on the x-axis are increased with our official outlook. And it gives you a quantitative way to understand how that shift, the forecast affects actual values and precipitation amounts. So we realize that that's almost impossible to understand for many users, and so we've developed basically a GUI interface to do what I was just showing you, or tried to show you the last few slides. And so what's shown here is what we call the POE calculator, or probability of exceedance calculator, and you can see there's a number of selections that you can make to select the product, and in this case we're try temperature for May, June, and July. And we're trying to focus on what the percent would be, knowing that 58 is the climatology, as I mentioned. This is, again, that Seattle area, as you can see in the upper far left of this particular image, what would be the percentage? Basically, the forecast is saying that there's 60.3 degrees, the probability of exceeding that is 20%. If we were to go to another way of looking at this on the next slide for total precipitation, you can do it by value. Again, this is that eastern Idaho region that I mentioned with precipitation. Again, you can select precipitation for a similar season, and you could try, instead of doing the percentile, you can look at the value. And if, say, you wanted to select, what are the odds, what's the percent of probability of exceeding some of the near record values in the distribution, which would be closer to, say, 7 inches or so, you could see that that's only 10%. So it's a very end part of the distribution. So this is a better way, we hope, for users to better understand and to get exactly what they're looking for a given area. Now, this is based on climate divisions. The goal will be to make this more on a grid basis in the future, but this is what we have so far. Now, some of the other things that we have available to help, provide some awareness of the type of outlooks we have. Past outlooks are shown. These are various website URLs here. For example, one can use the first URL link to take a look at any forecast going back to 1995 for monthly or seasonal, if you enter in the forecast year and month. The middle panel shows the verification of all those outlooks for the seasonal forecasts, which are shown here on the right, which shows the forecast, then shows the observations in the bottom part. You can download the various data sets, both observations and forecast, through that web interface as well, to help get a feel for individual seasons and how they did compared to observations. And finally, another web URL below here allows all of our forecasts to be downloaded as shapefiles or KMZ files for GIS-related applications for folks that are interested in that data as well. So I want to move on a little bit now to the kind of the basis for these outlooks, which I know many of you may be very familiar with, but I do think it's important when we move towards the verification that we're dealing with a very difficult endeavor here, where we have the signal to noise is quite low. And as we move forward, there's a number of things that we can use. One that I think everyone is very much aware of, what works better in certain areas than others, certain years than others, but basically you could see that in the second bullet is basically the ENSO state, which is the changing in the ocean temperatures in the in the equatorial Pacific, how those vary both in strength, persistence, and evolution over the course of the seasonal cycles is very important. We also can make use of, for example, in the first bullet, at times other boundary conditions, whether it be soil moisture anomalies, snow cover, or local sea surface temperatures and so on, to help us where they have some memory in the climate system. Now, we do try to look for other climate modes just besides ENSO, of course, but there's a lot of discrepancy and a lot of research that's still going on, whether these factors really play a role and how strong they play a role in a seasonal or interannual type forecast that we've been talking about here. For example, the Arctic Oscillation, North Atlantic Oscillation, and so on, certainly have variability on the weekly time scale. They have variability on the monthly and seasonal time scale as well. And so trying to understand if a particular index such as the AO or NAO, which can provide strong anomalous conditions in temperature and precipitation in certain parts of the CONUS, whether those are going to persist all winter long, for example, or not is just not really well understood and not very predictable really beyond a few weeks. Another thing that we were able to use also at times, especially with temperature, sometimes they are very strong trends, decadal variability, basically warming trends in certain areas in which those remain pretty robust. The next thing that we make use of, that's more of like a physical argument about things or basis. So trying to use some of that information, we very much make use of statistical and dynamical model forecasts. Now, there's certain predictors, if you will, in which statistical forecasts or empirical forecasts can be derived, and we have a number of those. And we also have a whole host of dynamical models now, which are basically weather forecast models that you may see on TV for the next 5, 10 days or so. But these are integrated out or run out in time to what's called maybe with a short-term climate prediction time scale, let's say over the next several months, 6 to 9 months, for example. And with that, we can do a whole host of things. We can combine information from all of these different forecast tools into what we can call an objective consolidation, which is based on information in the historical record, whereas the weights or the amount of confidence given to any one tool or a group of tools is based on historical forecast accuracy or forecast skill. And but the forecaster still can subjectively adjust those forecast maps that I was showing earlier. So for us, we have a team of seasonal forecasters that reviews all this information. I'll show us a few examples on the next several slides, but again, I don't want to go into a lot of the technical details. I'll be happy to answer that in the question section or offline afterwards. But our process is that we have, it starts basically a week-long process. Forecasters at CPC gather internally on the Friday before the release date to review the latest current climate state, previous forecasts, and we all draw generally preliminary maps for the first lead or two, depending on the situation. The forecaster, who is the lead forecaster, will go ahead and make all of those maps that I mentioned, 26 in total, 13 for temperature and 13 for precipitation. And on Tuesday, we have a conference call where that forecaster will present the recent verification of the outlooks, the current physical state of the climate system, whether it be the current situation or status of ENSO, to snow cover anomalies, to larger scale type modes such as the Pacific Decadal Oscillation or the AMO, for example, things like that, as well as show his draft maps for discussion. And that's about ends up being about an hour, hour and a half, back and forth on that. And then finally, the forecast after further iteration based on feedback from these meetings, the forecasts are released on the third Thursday of the month, 8:30 Eastern time here. And the one thing to note also is the ENSO forecast is always updated prior to the start of the seasonal process, just so that we have consistency among the ENSO forecast and also our seasonal outlooks. So I already talked about the next slide here, which is basically some boundary conditions that can apply, have some memory in the climate system, snow, soil moisture, and local SSTs in some areas. What's shown here in this slide is kind of an example of some of these different empirical statistical forecasts that I was describing. One, for example, on the right, which we like to use kind of as a good baseline, which is a combination of the long-term temperature trend, for example, plus the state of ENSO, in which we get from our objective Pacific Ocean temperature forecasts. And so that can be one tool that helps us from a statistical point of view. We have a number of different things. If you recall, a few minutes ago I mentioned we can combine things based on historical skill and general confidence. And so we can create a statistical blending of models, if you will, and also dynamical blending of models to get a final consolidation, which is an example here shown on the right. And so one could argue that this is kind of a serves as a good first guess. Very often that's what we'll end up doing. But after further debate and discussion, this will be modified or adjusted with time throughout that weekly long forecast process. One thing that we don't have any lack of are a host of dynamical or numerical weather prediction models that are basically operate on the short-term climate prediction timescale, meaning they are run out further in time, focusing on climate-related boundary conditions as forcings or predictors. And this just shows just a sample of all the different models that are available to us. This is a particular case from December of 2018. Not only do we have the individual models, which are shown in the bottom two rows here, where this is temperature, so above normal temperatures are indicated by the red shades and below normal by the blue shades, but we also have the top row, which shows in the upper left basically an equal weighted combination of the departures from normal for all of those models, which we call the North American multi-model ensemble. We can calculate or convert, if you will, that forecast into probabilities, which our outlooks are in, as I showed earlier, which is in the center plot. And then the plot on the right is in which we calibrate those probabilities based on historical skill and real-time forecast spread. So that's a way of us trying to find the most reliable signals to utilize for our official forecast. And as I mentioned before, one thing that is a strong predictor at times was what's called the longer term trend. And basically what that is, we define it as the optimal climate normal, or OCN. But basically all that is the difference between the last 15 years minus the WMO standard 30-year average climatology. And so sometimes the trends in certain areas for temperature, for example, are strongly positive. And so it's very difficult. It's actually a pretty good predictor at times in certain areas when there's other factors that are not currently in play. And for precipitation, the trends are generally much less overall, more sporadic and more difficult to define, but we also have that as well. So moving to the last section of the presentation is how do these forecasts do? And there's a number of different ways in which you can quantify how they do. One that we use is called the modified Heike skill score, and there's no need to remember what that name is or what, but there's a whole host of these. This is one that we use because it's relatively straightforward, and we hope easy for folks to understand. It's good for the categorical forecast that we do as far as the below normal, near normal, and above normal. And basically all it's saying, all it's trying to relate is what the percent improvement of over a random forecast or a climatological forecast in our case is. And so basically as you look at that equation, it's the number of correct hits over the expected number of hits, which would be 33% for a 3-class system, over what would be the total number of forecasts. And you can look at that later, but basically that score will go from -50 for a 3-class system to 100. And the best forecast is a score of 100, and a 0 indicates that you have no skill over what's expected from a baseline forecast. Sorry. And the -50 would be actually you've gotten none of the areas correct. So you want to have higher positive values wherever possible over the majority of your forecast domain. So the slide I'm showing here is the one of our government performance metrics that we need to show report on every month, and it's for U.S. seasonal temperature. And this metric is actually a 48-month average score for our Lee 1 seasonal temperature outlooks, which is what's shown in blue. And the goal from headquarters is the yellow triangles. And so this goes from September 2002 on the left, and all the way out to almost to basically the most recent forecast verification that we've had. And overall, you see an upward trend. There's a lot of variability with it, as you can see. through most of the period. During the later part or early part of the fiscal year 18, we actually had a record value for this metric of about 44. We've since come down since then, but in general, overall, the trend has been up. But again, there's a lot of variability with it. And what's shown here are the areas that are non-EC, or the areas in which we've made a forecast for. So that's important to note. The plots that I'll show in the next few pages will be for the whole grid area. And so those are just by definition smaller, but basically the trends still apply. And if you go to that next plot, which shows that Heike skill score, but again, this is for all areas, so the values will be lower, or about half of what is typically shown for the non-EC areas, which is what the previous slide was. But this is for temperature, seasonal temperature, all seasons, from 2010 to 2019. So it's a relatively short sample, but it has all 12 overlapping seasons in them. And overall, most areas have positive skill. The highest values in the orange and red areas are across much of the west, parts of the south, and also along the eastern seaboard in some areas. Unfortunately, which is not a surprise to many people, I think, where some of the ENSO signal can be very, for example, one of our main predictors can be ENSO. Some of the scores are just slightly positive or near zero in the interior, but all are slightly positive, again, along the northern tier of the central region area, northern plains region, into parts of the Great Lakes. And this is for temperature for all categories. Now, for precipitation, from a spatial point of view, precipitation, no matter what time scale you look at, day 1 to seasonal, precipitation is much more difficult to predict. Scores are always lower because it's not continuous in time and space at any time scale, and it proves to be very difficult. For us, we do have positive skill overall, but mainly across the west and the southern areas, and to a lesser extent across some areas of the Midwest. But we actually are basically have little skill across much of the northern plains because of the variability, whether it be ENSO or not, plays a large role in the eventual verification of temperature and precipitation in that part of the country. On the next two slides are just the time series. Again, these values are lower than what I showed on that first slide because these are all grid areas. But in general, on average, the score is positive, which is good, but lots of variability. The last few scores have been on the negative side, but we have been on a very good roll of only a few negative scores dating back to 2014. And then for our precipitation, as you would expect, it's a challenge. Again, there are certain years and certain periods of years in which we have positive skill and are able to say something useful, but and overall the score is positive when you look through the whole year of this 10-year period. But there's quite a bit of variability, similar to temperature, and also more, unfortunately, in the way of zero or negative values of the Heike skill score, indicating there's no skill. So I think I'm going to end there, a little bit over, but I really do want to, again, thank everyone for their attention and time, and take any comments or questions or suggestions if you have any. Thank you very much.
Okay, thanks, John. I'm going to go ahead and pop up the second poll question, and then we do have a couple questions in the chat box. And then if anyone else has some, go ahead and bounce those in that chat box, and I'll ask them. First one's from Mark, and he said that it seems like some of these maps are blurring the lines between climate and weather prediction, and asked where you guys draw the line.
Yeah, that's a great question. That's actually something that we've had a number of discussion points with management, whether it be here at CPC, at NCEP, or actually at Weather Service headquarters. And right now, we're officially, with respect to the weather bill, are on the order where we still are responsible for the week 2 forecast all the way out to 1 year. And so even though the weather forecast models, if you will, and ensembles are becoming increasingly better, there still is a drop-off in skill on the order of like day 7, day 8 or so, where there's some information in which ensemble methodologies and also background climate modes that act on the subseasonal still can play a part in how you adjust your forecast. For example, certain states of ENSO or the MJO, for example, or of course the higher latitude types of variability, whether it be the Arctic Oscillation or the North Atlantic Oscillation or so on, can tilt you one way or another. So this climate weather linkage period is a very good point, and it's somewhere during week 2. It's also been discussed quite a bit in the concept of coupled modeling. For example, when does coupling with the ocean and certain models and ensemble systems matter? Does it start to matter in week 3? Does it matter during week 2? And so on. And so it's a very difficult question to ask. But again, our mandate still is to provide these forecasts in the week 2 period. So that's what we're doing.
Okay. One more here, actually a couple more, but one more now. Do you have plans on making some of your maps, such as the 6 to 10 day and 8 to 14 day outlooks, more user-friendly for social media use? And that question was from Theodore.
Yeah, that is correct. We have ongoing activity right now that we hope to be able to complete that type of work by the end of the calendar year. If not by then, shortly thereafter. We're definitely working on that.
Okay, and then Wendy had a question that she may have overlooked this, and I think you may have had it on there. I'm not sure. The web address for the GUI and POE calculator. I don't know if we had that on the slide or not.
Yeah, I think that I forgot to do that. So I apologize. I can send that to you, Tyler, and you can send that out. Sorry about that.
Okay. Yeah, no problem. That's the last question that I have, at least listed on here. You kind of touched on the social media question already, but I had a question. I see lots of a lot of these forecast models that go out past the 7 days, 10 days, 14 days, and they're readily available to people that might not understand the complexity that goes into a model and how to use them. And I see it a lot during social media, and especially when it comes to a snowstorm that's 10 days out, and you get the 36-inch forecast. And so it's some of those things are easily to share on social media. So it's nice to see you guys ramping that up.
Yeah, and we do. Yeah, very good point, Tyler. And we do have a number of different venues, whether it be the Weather Service Twitter feed or other areas, Facebooks, or also we do have a number of. We have a Facebook page ourselves and a Twitter feed that we tend to try to send those sorts of things out too, just in the sense of trying to provide, I guess, for lack of a better word, an official assessment from the Weather Service for that week 2 period. And same thing for the more of the snow amounts that are more applicable for the shorter term, like WPC, for example, Weather Prediction Center. They tend to, so we've been trying to fight that a little bit, but it's hard because everyone who can do that will pick their favorite model if they want snow or if they don't want snow, and they will basically, as an example, and they will tweet or put that on Facebook, and it's very hard to control. So all we can do is try to send out through social media and our regular web outlets what we think is the most responsible forecast, as being kind of like an honest broker. We're not trying to make money or not make money off various forecasts. And so in that paradigm, that's how we try to operate.
Okay, thanks. Mark has another question in relation to Canada. It says some of the maps had data for Canada, but most of the maps do not, at least the finished products. He mentioned it'd be nice to see some of the maps with color coding for Canada, and didn't know how hard that is to do.
Yeah, what we were trying to do is that we did a social science project this past 2 years, which relates back to Mark's earlier question in the sense that to make our graphics more user-friendly and so on. And so that's part of it. The other part of it was to try to make it more compact, if you will. At least this is what was recommended by the users in the study was to actually have insets for Hawaii and Alaska, for example, and just have the continental United States so that there wouldn't be any confusion with respect to Canada, because officially we're not able to provide official forecasts for Canada as they have their own weather and climate services. So that was one way it was recommended to us as part of the social science project to handle that. But that's just one strategy that was proposed.
All right. One more question from Wendy in relation to the 8 to 14 day forecasts. Are they created each day, and are they adjusted by forecasters, or are some of them computer generated?
Yeah, first question is they are available each day. And the second question relates to that, in that during the Monday through Friday period, what we basically have, actually to all the days, is with some of the model guides and forecast tools we have, we combine them, as I mentioned, based on pretty quantitative, rigorous methods to get what we call first guess map, if you will. But the forecaster will adjust that based on any other various factors. For example, sometimes some of the forecast tools may be playing too much a certain bias that's occurred when we're in a transition, things like that. And so the forecaster will adjust some of the probabilities based on that. But it does start from, which, at least for the most part now, it does start from an initial first guess, objective, skill-based map that can be adjusted by the forecaster. On the weekends, we tend to have a very similar approach, except that there's no message, or there's no text discussion that's provided on the weekends. It's just the forecast maps. Again, driven same process.
All right. A question from Mark. How much do you work with the flood prediction folks?
Very good question. Is that in the past, not very much, but in the last year or so, that's ramped up considerably. We've had a number of folks visit the RFCs in different regions, whether it be, I forget all of them, but actually our director had visited almost all of the RFCs across the country. And so what we're trying to do is feed in some of our longer range outlooks, whether it be from week 2 on, into some of their flood forecasting models, and also working, of course, with the National Water Center and making use of that information in some of our longer range outlooks to start to look at whether we can provide more extreme type forecasts as we get beyond the week 2 period. So we have a number of projects going on now that are evaluating the National Water Model forecast, some of the tools that we have with respect to soil moisture and so on. And so we're a ways from that, but our interaction with them has increased dramatically in the last 1 to 2 years.
All right. I don't see any more questions popping up, so I think that may have gotten them all answered. So thanks again for joining us and for doing this. It's insightful always to see the back end of some of these things that we think just pop up out of nowhere every day, right? So it's good. So it's good to see some background into that. So thanks again for doing that. I appreciate it.
You're welcome. Thank you for the invite. And hopefully, if anyone has any further questions, they're very welcome to email me if I glossed over something and they didn't understand it. So again, I appreciate everyone's time. Okay,
great. We'll go ahead and end with that. And the recording will be available here probably in a couple days. We'll have it up on the website. So have a nice day, everyone.
Okay. Bye-bye.